Hello everyone, welcome to the chemistry channel. So today we are going to be starting our 5th lecture on atomic structure, and we are closing in on actually discussing atomic structure. So today we're going to be talking about two very important topics. The first topic that we're going to be talking about is the Schrödinger equation. So we're not going to be getting pretty much at all into the mathematics of it. We're only going to be getting into the qualitative concepts associated with it. We're also going to be talking about quantum numbers and how to use them and how to interpret them. So it's going to be a very useful video, and it's also going to be a very interesting one. So with that, let us begin with our concepts for today. So at the center of all quantum chemistry, all of the understanding of atomic structure, is this branch of physics called quantum mechanics. And quantum mechanics is a branch of physics that uses the dual nature of matter in order to understand the world. So as you may remember, the dual nature of matter basically states that all moving matter has both particle-like and wave-like properties. And this idea has been applied to chemistry. So quantum mechanics, this stands for quantum mechanics, has been applied to chemistry. So recall that moving matter has both wave-like and particle-like properties. And we showed this through the de Broglie relationship, or the de Broglie wavelength equation, where the wavelength is equal to Planck's constant over mv, which is equal to Planck's constant over the momentum. And we talked a lot about this in the last video, so if you are confused about that, please go to lecture 14, where we talk a great deal about this equation, and we actually derive it as well. So at the center of all of quantum mechanics is an equation called the Schrödinger. So the Schrödinger equation. So the center equation of all quantum mechanics is the Schrödinger equation. And it's from this Schrödinger equation that we actually understand atomic structure. So it is unlikely that a general chemistry class will focus on the equation itself. But however, I think it's pretty cool to just show you what the equation looks like and describe to you what the different variables are. So this right here is the famous Schrödinger equation. So let's talk about what each of these variables are. So the first variable is the Hamiltonian operator. So the Hamiltonian operator. And the Hamiltonian operator is basically a mathematical operation that allows us to extract the energy from a system. So it provides us information about the energy within a particular system. The next bit of information that you should know about and that you should have an understanding of are wave functions. So this is the symbol for a wave function, and this is something that you should know. A wave function is a function that comes out of the Schrödinger equation, and they are basically used to describe the wave nature of particles. So they are functions that are used to describe the wave nature of particles. And the last bit of information is E. E stands for the total energy. So once again, you're probably not going to be required to know the Schrödinger equation because the difficulty associated with it is far above the level of any general chemistry class. So therefore, this is just to give you an appreciation for the equation and to have an awareness of it. But however, I think it is important to have a qualitative understanding of the equation. So with that, let's describe what the equation implies and how it was developed by Schrödinger. So the Schrödinger equation treated electrons of the H atom, so it's important to note that this is from an H atom, as a standing wave. So Schrödinger treated the electron of an H atom as a standing wave. So if you are in physics, you may know what a standing wave is. However, if you don't, that is okay. A standing wave is a wave that does not travel through space. So it's not like a sound wave going through the air. It's not like light. It doesn't really travel. Instead, what it does is it can bounce back from a surface back to its point of origin, but that's beyond the scope of this course. A standing wave, a good example of a standing wave is imagine tying a jump rope to a tree and basically waving the jump rope up and down. Now, when you do that to the jump rope, you are actually creating a wave. However, the wave itself is not moving anywhere, so therefore it's called a standing wave. So a standing wave is a wave that does not travel or move anywhere. So Schrödinger uses his understanding of standing waves in order to describe electrons. So I think it's important to have a rudimentary understanding of standing waves. So in this figure, I have 3 different standing waves. So let's look at this first figure here. This first figure shows the fundamental frequency. So the fundamental frequency. So what is the fundamental frequency? Well, the fundamental frequency is the lowest frequency of a wave that can be supported. So it's the absolute lowest frequency of a wave that can be supported. So that is the fundamental frequency. And the fundamental frequency is given the name n equals 1. Now, the important thing to note about the fundamental frequency is that the fundamental frequency also has the lowest energy. So the fundamental frequency also has the lowest energy associated with it. So let's look at the next figure here. And as you can see, this next figure has clear differences from the first one. And the main difference here is this point of intersection. Now, this line here, the pink line, you may remember from my Properties of Light video, is the equilibrium position. And the equilibrium position is the position at which the wave oscillates around. So the area of the equilibrium position where the wave intersects is called a node. So this little area is called a node. So nodes can be seen where the wave intersects the equilibrium position. So this is a node. So let's define what a node is. A node is an area on the wave that has no displacement in amplitude. So in other words, the node does not oscillate. It sort of just stays there. So that is a node. And this type of wave where you have one node here, this one node here, is called the first overtone. And this is given the symbol n equals 2. And the first overtone has a higher frequency than the fundamental frequency. Therefore, the first overtone has a higher energy than the fundamental frequency. And then the last bit here, we see that we have two nodes. So here's a node, and here's a node. And these two nodes here, show that we have a higher frequency than the first overtone. And this overtone is called the second overtone. And it is given the name n equals 3. So this is the second overtone, and it has the highest frequency out of these three different standing waves. So let's summarize what we learned here. So as we go from top to bottom, the frequency increases. And as the frequency increases, as the frequency of the wave increases, the energy increases as well. So we also increase in energy from top to bottom. And this should make sense to you, because in one of the last videos, we described that the energy of a wave is directly associated to its frequency. And Planck showed this through his quantization of energy, which states that E is equal to Planck's constant times F. So therefore, as the frequency increases, the energy also increases. And we can see this here. As the frequency increases from the fundamental frequency down, so does the energy of the wave as well. So Schrödinger used this idea of standing waves and applied it to the electron within a hydrogen atom. Now recall that electrons can be described as waves. Now because electrons are described as waves, they can also be described by wave functions. And remember that wave functions, so let's get this little line out of here. So wave functions basically come out of the Schrödinger equation. So this means the Schrödinger equation when you solve it. And we already talked about this earlier in the video. So wave functions are these functions that come out of the Schrödinger equation when you solve it. Now, in order to get useful information out of the wave function, you must square the wave function. Now, this is another topic that you must be aware of. When you square a wave function, what you get is basically a probability function. So in other words, a wave function squared describes the probability of finding an electron in a location. So it describes the probability. So that's important to stress, that it describes the probability of finding an electron within a particular location. So probability is different from exactly knowing something. So therefore, we cannot exactly know the exact location of an electron. We can only state the probability. Oops, sorry about that. Let's get rid of that. So we can only state the probability that an electron occupies a certain space. So this is why we actually say an electron. This is why we say atoms are surrounded by a cloud of electrons. So what do I mean by, whenever I say this, what do I mean by a cloud of electrons? Well, because we can only describe the probability of an electron being in a certain place, we can only map out probability densities. So probability density. So in this figure, I am showing you an example of a probability density. So in this figure, you see all these green dots, and these green dots correspond to the probability density of the atom. So what is the probability density? The probability density basically describes the probability of finding an electron in a certain location of the atom. So it's basically describing the probability of finding an electron within a certain location of the atom. So how do I interpret this graph here? Well, areas in which the green dots are thicker correspond to higher probability densities. So darker areas correspond to higher probability densities. So in this particular graph, the area with the highest probability density is in the middle. And lighter areas correspond to areas of lower probability density. So as we move from the inside of the atom to the outside, we see that the probability density of this particular species here decreases. So we'll say on this blue line here, decreasing probability density. Okay? So this darker region here corresponds to higher probability density, and these lighter regions here correspond to lower probability densities. And that's why we say that atoms have a cloud of electrons, because by saying we have a cloud of electrons, instead of saying that we know where an electron exactly is, we can map out instead the probability of the range of locations that an electron can occupy. So by saying we have a cloud of electrons, we're basically mapping out the certain probabilities of an electron occupying a certain space. So that's why we say electrons have a cloud. That's why we say atoms have a cloud of electrons. So now that we have a basic idea of the Schrödinger equation, let's actually talk about quantum numbers now. So let's change my color here to something else. So let's use red. So wave functions, so the wave functions that pop out of the Schrödinger equation correspond to orbitals. So the wave functions that pop out of the Schrödinger equation correspond to particular orbitals. So what is an orbital? An orbital is a probable region in which an electron can occupy. So it's basically a probable region in which an electron can occupy. And each orbital has a characteristic shape and energy associated with it. So in this video, we're going to be primarily talking about the energy of each orbital. However, in the next video, we're going to be talking about the different shapes. So in this video, let's get into the three main quantum numbers. So I've already stated it here that there are three main quantum numbers. And the first quantum number is the principal quantum number. And the principal quantum number is given the symbol n. So the principal quantum number is given the symbol n. And we actually introduced this already in the Bohr video about the Bohr model. So the value n, so n can have only positive whole number values. So in other words, it can only have values of like 1, 2, 3, 4, all the way to infinity. So n can have only positive whole number values. And as the value of n increases, the energy increases as well. So as n increases, the energy increases. And we actually already saw this in our Bohr model video when we talked about E is equal to negative 2.18 times 10 to the negative 18th times 1 over n squared. So as you can see here, as n increases, the value of energy becomes less negative, therefore allowing the total energy to increase overall. So, however, as the value of n increases, the energy increases. But also, as the value of n increases, the size increases as well. So the size increases as well for the orbital. So as the value of n increases, the size of the orbital increases as well. So this is the size of the orbital. Okay, so what does this mean about the size increasing? As the size of the orbital increases, the probability of finding an electron further from the nucleus increases as well. So therefore, as the size of the orbital increases, the probability density, or the probability of finding an electron further from the nucleus, also increases. So that is the principal quantum number. It basically describes the overall energy of a particular orbital. So the next part that I want to discuss is the angular quantum number. So what is the angular quantum number? Well, the angular quantum number is given the symbol L, and the angular quantum number, so I'm just going to say it like this, is the quantum number that gives the shape of the orbital. And we're going to talk more about the shape of the orbitals in the second video. So it's important to note a certain formula that the highest angular quantum number, an energy, let's actually say that an energy. So let's erase this. So the highest angular quantum number that an energy level can sustain is equal to n minus 1. So for example, if you had a energy level equal to 2, so if your principal quantum number was equal to 2, the highest angular quantum number you could have is 2 minus 1, which is equal to 1. Now there's a certain chart that you have to memorize in order to answer the problems associated with the quantum chemistry. So here's a chart. I'm going to draw it out for you. Now for each quantum number, there is a specific, for each angular quantum number, there is a specific letter associated with it. So here I'll put the values of L, and this little area is going to be for the letters. So I'm just going to shade this in. So if your L value is equal to 0, we call that L value S. If your L value is equal to 1, we call that particular L value P. If your L value is equal to 2, we call that particular L value D. And lastly, if you have a L value of 3, we call that particular L value F. So this is what you'll have to memorize, because this is going to be very important for when we get into electron configurations and atomic structure. So the last little quantum number that you have to know is the magnetic quantum number. And the magnetic quantum number is given the symbol ML. And what does ML tell us? Well, ML tells us the orientation of an orbital. So what is ML equal to? Well, ML, the numbers, you can have multiple numbers of ML. So ML is equal to the negative value of L all the way up to L. So for example, if I had a value of L equal to 3, how would I draw this? Well, I would draw this like this. So I would draw 1. So if 3 is equal to F, so that would correspond to 7 different orbitals. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So why would there be 7 orbitals? Well, it's because each orbital corresponds to a magnetic quantum number. So therefore, I would label these orbitals as -3, -2, -1, 0, 1, 2, 3. So these are all possible values of ML, or the magnetic quantum number. And we're going to get into this in a little bit more in detail. So those are your 3 main quantum numbers that you should be worried about. So the last thing that we're going to get into today before we get into the practice questions is the hydrogen atom. So Schrödinger used his ideas in order to describe the electron within a hydrogen atom. So there's 2 main definitions that you have to be aware of. The first is the electron shell. And an electron shell is a collection of orbitals with the same quantum number. So actually, let's change this to the same principal quantum number. Principal quantum number. And a subshell is a shell within a particular energy level that indicates the angular quantum number as well. So it will indicate the angular quantum number as well. So for example, an electron shell could be described as the n equals 3 energy level. And the subshell could be represented as the 3s orbital. So the subshell is more specific than the electron shell or the energy shell. So let's talk about the hydrogen atom. So here is a figure showing the particular energy levels associated with the hydrogen atom. So the first thing that you should note is the separation of the different energy levels. And this should correspond to what we learned in the one of our last videos when we talked about when we talked about the separation of energy levels and the line spectra. So as you'll notice here, as the values of n increase, the difference between energy levels decrease. So as we go up, the differences will continue to decrease and decrease and decrease all the way up to infinity. So the differences between the energy levels decrease as we go up in the energy shells or the electron shells. So the second thing to note is that on this diagram here, we show both the electron shell and the subshell. So the n equals 1, n equals 2, n equals 3 correspond to the electron shells. So all of these little values here described by the principal quantum numbers correspond to electron shells. These little orbitals present within each of the shells correspond to subshells. So this little orbital here corresponds to the 1s subshell. So what does 1s mean? 1s means that you have a orbital within the n equals 1 electron shell and within a angular quantum number equal to 0. So remember, that's because s is equal to 0. So in the n equals 2 shell, we have a 2s subshell and a 2p subshell. So within the 2p subshell, we have so for the 2s subshell, we have an n equals 2 electron shell with an L equal to 0. And for the 2p, we have an energy electron shell equal to, for n equals 2, and an L value equal to 1. And then lastly, we have a n equals 3 electron shell. So each of these subshells has an electron shell equal to 3, or energy level equal to 3. And each of these subshells can also be characterized by its angular quantum number. So 3s, what does that mean? An L equal to 0. 3p is an L equal to 1, and 3d is an L equal to 2. And this also shows you our rule, that the maximum angular quantum number is equal to n minus 1. So now let's label the mLs on each of these subshells. So the first subshell that I want to label is the 1s. And here we have an L value equal to 0. So therefore, according to our rule for magnetic quantum numbers, negative L to L, we label this particular orbital as 0. Now, if we move up to the second electron shell, n equals 2, we have the 2s shell. So what will we label this orbital? 0. Now, the 2p has an L value equal to 1. So following our rules of L, negative L to L, we can label the 2p as negative 1, 0, and 1. Now, as we move up to the third electron shell, we have our 3s orbital. Since it has an L value equal to 0, we can call the magnetic quantum number of this orbital 0. So we just also copy the same thing from our previous orbital. And then for our 3d orbital, we see that L is equal to 2. And following our rule, negative L to L, we get negative 2, negative 1, 0, 1, 2. So the last thing to note for the H atom is that every single energy electron shell has degenerate orbitals. So these orbitals are degenerate to each other. So these are degenerate. These orbitals are degenerate. And since there's no other orbitals here, we're not going to call this one. Well, this is degenerate too, to itself. So what do I mean by degenerate? In an H atom, all of the particular subshells are degenerate to each other. So in other words, the 2p orbitals are degenerate towards the 2s orbital. And the 3s orbital is degenerate towards the 3p and the 3d orbitals. So what does degenerate mean? Degenerate means equal energy. In other words, all of these orbitals within each subshell have the same energy. Now, it's important to note that the 1s orbital has less energy than the 2s, the 2p, the 3s, the 3p, and the 3d. However, it's also important to note that the 2s orbital has the same energy as the 2p orbital, and the 3s orbital has the same energies as the 3p and the 3d. So all of the subshells within a particular energy level are degenerate in an H atom. So degenerate means the same energy. So why are the orbitals within the same energy level? So this is only talking about orbitals within the same energy level. So only orbitals within the same energy level are degenerate. So why are orbitals within the same energy level degenerate in an H atom? Well, it is because, so this means because, there is only one electron in an H atom. So why would one electron produce these degenerate subshells? Well, it's because if you have only one electron, there is no electron-electron repulsion. Because think about it. If you have multiple electrons in the same energy level, negative charges don't like to be with each other. So if you force these electrons to be in the same energy level, the orbitals no longer become degenerate because of the electron-electron repulsions. The electron-electron repulsions cause the electrons repel one another, which therefore requires the orbital to have a more different amount of energy than the other orbital present within the energy level. So in this case, the 2p orbitals, since it has electrons within in a greater proximity of each other, would be greater energy than the 2s because you have multiple electrons with each other. However, if you only have one electron, this repulsion does not exist. That's why That's why the subshells within a particular energy level are degenerate, because there is no electron repulsion in order to increase that energy. Now we're going to talk more about this when we apply these ideas to multi-electron atoms. So this is going to make more sense when we go into that. But the important thing to note for this video is that orbitals within the same energy level are degenerate, and that is in an H atom. And that is because there is only one electron in an H atom. And this is true for any one electron species. So one more thing to note is the ground state and excited state for an H atom. So let's put in parentheses for an H atom. So the ground state for an H atom is when an electron occupies the 1s orbital. And that is because the electron is in the lowest energy orbital. The excited state is when an electron occupies an orbital of higher energy than the 1s orbital. So when your H atom's electron occupies a orbital higher than the 1s, so in this case a 2s, 2p, 3s, 3p, 3d, etc., then we say that that electron is in the excited state. So that is it for all of the concepts today. So in order to conclude for today, I have 2 practice questions for you. One of them is a multiple choice, and the other one asks you to write all the possible quantum numbers for the n equals 4 energy level. So I encourage you to pause the video and try these for yourself. These questions are very reflective of what you would probably get on an exam. So I encourage you to pause the video and try them for yourself. And when you come back, we'll do them together. So hopefully you pause the video and try them for yourself. So with that, let's do this first question. So the first question asks you, what are all the possible quantum numbers for the n equals 4 energy level in an H atom? And I ask you to also please draw the orbitals. So let's just give myself we can do this in this space. So in order to do this, we have the n equals 4 energy level. So the first thing that you can do is maybe write n equals 4 just to start off. And then you can maybe put your little energy diagram here. So this is our energy diagram. So the first thing to note is that in order to find all the possible quantum numbers, you have to know the maximum the maximum angular quantum number that you can get for the n equals 4 level. So in this case, the max angular quantum number that you can get for the n equals 4 subshell is equal to n minus 1. So therefore, when you subtract 1 from 4, you get 3. And now the angular quantum number of 3 corresponds to the 4f orbital. So therefore, we can have orbitals all the way from s to f. So the first orbital that I'm going to write is, so actually let's write this. So we can have orbitals with an angular quantum number equal to 0, 1, 2, and 3. So let's draw what this would look like. So the first orbital that we would have is a 4s orbital. And now this 4s orbital has a magnetic quantum number equal to 0. Why? Well, it's because the s orbital has an angular quantum number equal to 0. And since the range of MLs, or the range of magnetic quantum numbers that you can get for a particular set of orbitals, is equal to negative L to L, so let's put a little negative here, that's a negative. The only magnetic quantum number that we could have, is an ML equal to 0. And this S is equal to an L equal to 0, so you have the quantum numbers. Now it's important to note that all energy levels, that all subshells within a particular energy level in an H atom are degenerate. So therefore, the next orbital that we would talk about is the 4 p orbitals, and they would be the exact same energy level as the 4s orbitals. So they're the exact same energy because we're only talking about one electron. So these are the 4p orbitals, and this would have an angular quantum number equal to 1. So therefore, our range of magnetic quantum numbers, which is equal to negative L to L, would be negative 1, 0, and 1. So we just write that here, negative 1, 0, 1. So the next range of orbitals would be the 4d orbitals, or an L equal to 2. So in this case, the 4d orbital, we have 5 4d orbitals. So 1, 2, 3, 4, 5. So let's actually make these a little bit straighter. So 1, 2, 3, 4, 5. And these correspond to the 4d orbitals, right? So the 4d orbitals would have an angular quantum number equal to 2, which means that we would have a magnetic quantum number range from negative 2 all the way to 2. So we just write negative 2, negative 1, 0, 1, 2. And these are all of your magnetic quantum numbers that you can have. So the last one that we can have is an angular quantum number equal to 3. And this would be the F orbitals, the 4F, and we can have 7 of those. So 1, 2, 3, 4, 5, 6, 7. And these would be your 4F, which correspond to an L equal to 3. Therefore, our magnetic quantum numbers would range from negative 3, negative 2, negative 1, 0, 1, 2, 3. And that is your answer for this question. Now, the main thing to note is that all the energy levels, all of these subshells within this particular energy level are degenerate in the H atom because we only have one electron. All right, so let's go on to the second problem. So in the second problem, I ask you to circle the choice that shows the correct set of quantum numbers for an electron within the n equals 3 level. So in order to do this, let's actually write all of the possible quantum numbers that we can get for the n equals 3 level. So let's write our energy diagram. And we have n equals 3. So this is the n equals 3 level. So we always start off with 3s. So we get our 3s orbital because when we find out the maximum angular quantum number, so the max L, which is equal to n minus 1, n minus 1, so we do 3 minus 1, the max angular quantum number that we can get is 2. So we would go all the way up to the d sublevel, to the d orbitals. So now that we have 3s, we can go, which corresponds to an L equal to 0, an n equal to 3, and an ML equal to 0. So now let's go to the 3p orbitals. So 1, 2, 3. So here is our 3p orbitals, which corresponds to an energy level equal to 3, the angular quantum number equaling 1, and the ML values ranging from -1, 0 to 1. So let's label these. So 0, -1, 0, 1. And then the last bit is the 3d orbitals, which are 1, 2, 3, 4, 5. So therefore we get 3d, which corresponds to an energy level equal to 3, L equal to 2, and therefore our ML values ranging from -2, -1, 0, 1, 2. So let's label these here. So -2, -1, 0, 1, 2. So now we just got to find a choice that matches the particular sets of quantum numbers that we generated. So the first thing is that we can eliminate choice A, because first of all, it's impossible to have an angular quantum number that's higher than your principal quantum number. So A is garbage. So let's get rid of another one. So B is also a garbage answer because you cannot have a magnetic quantum number that is greater in magnitude than your L quantum number. So therefore, this answer is garbage as well. So now, the only thing that we have to do is decide between these two choices. And D is also a garbage answer because you cannot have an ML value or magnetic quantum number that is greater in magnitude than the magnitude of your angular quantum number. So therefore D is garbage as well. So the correct answer is C. And if we check to see that these numbers correspond to a correct set of quantum numbers, we can actually see that we are correct. So first of all, this answer is correct because it says we are in the n equals 3 energy level, which is correct. And then we go look at our angular quantum number, which says an L is equal to 2, and this corresponds to the D, 3D sublevel. So therefore, and we look at our 3D sublevel, and the 3D sublevel contains magnetic quantum numbers from -2 to 2. So therefore, it should contain a magnetic quantum number equal to -1. So therefore, C is correct. So guys, that is it for today. That was a longer video. I hope I helped you. I know this can be confusing stuff. And if you have any questions associated with this, please ask me in the comments section. I know that this stuff is very difficult to understand, and it's actually kind of hard to explain too. But I hope that my explanations were sufficient enough for you to understand the material better. So if you have any questions, please ask them in the comments section. And I hope to see you in the next video, because in the next video we're going to be talking about the shapes of particular orbitals. So it's going to be cool stuff. So I thank you guys for watching, and I hope to see you next time. See you around, guys.